We're now going to look at how to find the area under a curve using calculus. So in this case, we'll be using integration. And this is an exam question, or it's off a mock paper from Bury College A level. So what we've got is we've got a diagram with a curve, which is given by this equation, x squared minus 8x plus 20. So that's the curve there. And we've got the line y equals x plus 6. So this is the straight line. And what we're going to eventually do is find this area in red. But what we're going to have to do is find it as a compound area. So in other words, we're going to find the area underneath the straight line. So that would form a trapezium. And once we found the area of this trapezium, so in other words, it looks something like this, the area of the trapezium, which is between A and B. Once we'd found that area, what we could then do is find the area under the curve. So if we find our curve, then between the points A and B, the curve looks like this. A and B, and we can find the area underneath that for which we would use integration. So the area underneath this would be found by integrating y with respect to x between these 2 points, these two limits. So it's a definite integral between these 2 points. So I'm just going to go through the question in the order that it's asked here. So we've got part A, which is saying use an appropriate algebraic method to find the coordinates of A and B. So the first thing we need to do is find these 2 points. And what we've got is where these 2 points are would be where the y values of the curve and the line are the same. So we can equate them. So we can say, well, at the points of contact here, then we can say that x squared minus 8x plus 20 is actually going to be equal to x plus 6 from the other equation, the equation of the line. So this is a quadratic. If we make it equal to 0, then what we'll get is x squared minus 9x, and then take away the 6 from both sides will give us 14 equals 0. And then we could just solve that on the calculator or factorize it. So we've got x and x if we do the factorization method, x and x at the start of each bracket, and it's going to be multiplied to make them 14 and adding to make the minus 9. So we can see that minus 2 and minus 7 would do that. And so that means the solutions would be that x was equal to 2, which is xa as it's asked for in the question. So xa. And we can see that xb would be 7. So that's the first part done. And what we want to do is find for part B, this is going to ask us to find the area of the trapezium. So we're looking for the exact value of the area of the finite region bounded by the x-axis, so the horizontal axis here. The lines x equals xa, so this dotted line, and x equals xb, this other dotted line, and also the line AB. So this is the straight line at the top. So it's the area of this trapezium. So in order to achieve this, we're also going to need to find the y values at these 2 points. And that's quite easy to do because we can just use the straight line equation. We can say y is equal to x plus 6. So ya is equal to the xa value, which is 2, plus 6. So that gives us 8. And yb is using the xb value. So that's going to be 7 plus 6 is 13. So that actually means that our two coordinates are 2, 8, and the other one is 7, 13. So if we add these values onto here, we can see that just looking at the x coordinate, you can see this one is 2, this one is 7, and then the y coordinate, the y value, is going to be, so I'll put this on this graph actually, the y value is going to be 8 for A, and for the B, it's going to be 13. So to find this area, we can use the formula that the area of a trapezium is given by h, which is the height, which we actually mean this distance here, h over 2, and then the sum of the two parallel sides. So we could say A and B is what it would be in the formula. So A and B are the two parallel sides. So we know that our h is actually the distance between 2 and 7. So it's 5 here. So it's 5 over 2. And then A is this distance, well, because this has got a y coordinate of 8 and 0 at the bottom. So A is 8. And B, again, that's 0 at the bottom and a y coordinate 13. So it's going to be, actually a bit plus there. It's going to be plus 13. So what we've got is 5 over 2 times by 21. And that actually works out as 105 over 2, which is 52.5. So that's the exact value of the area bounded by AB and the x-axis. So that's part B done. So if we now look at part C, we've got to find the area under the curve between A and B. So bounded by the lines where x is equal to xa, so that's that dotted line again, and where x is equal to xb, so this dotted line. So it's this region here underneath the curve. So to do that, what we're going to do is we're going to integrate the line there, the curve. So we're going to do the integral of the curve y here between x equals a and x equals b. So we're going to do a definite integral, and it's with respect to x. So I can replace the y by x squared minus 8x plus 20. So what I'm going to do, I'm going to get this, x squared minus 8x plus 20 dx. And it's between the values that we got for xa, which was 2 for xa, and it was 7 for xb. So if we do that integration, then what we're going to always do for x to a power is we're going to raise the value of the power by 1 and then divide by the new power. So if I do that, then I'm going to raise the 2 by 1. So it's now going to become x cubed. But now we're going to divide by the new power as well. So it's going to be x cubed over 3. And then got the minus 8x there. And if we raise the power by 1, it now comes up to a 2. So we're going to have 8x squared over 2. And then if we're integrating a constant, so 20 is a constant, it's just going to be 20 times x in this case because it's dx. And now we use the square brackets. So this is the convention. And then you write the limits here. So 7 and 2. So what it is, it's just a case of substituting in the value 7 into this expression, and then working out the value of that, and then substituting the value of 2 into this expression, working out the value of that, and then finding out, subtracting the second one from the first one, and that gives you the area under the curve. So if we do that, first of all, I could just tidy this up so we can make this just 4x squared. So 8 over 2 is 4x. So we're writing it on a new line there. And so if I substitute in, then what I'm going to get is 7 cubed over 3. I'm going to open a bracket here. Minus 4 times 7 squared. Plus 20 times 7. And then I'm going to subtract from it another bracket where this time x is replaced by 2. So if I do that, I've got 2 cubed over 3 minus, and then we're going to have 4 times 2 squared plus 20 times 2. And so we just work all that out, and I get for the first bracket 175 over 3. Second bracket, which we're taking away, is 80 minus 3. And so if we then just work that out, we can just subtract top lines because the denominators are the same, then that's going to be 95 over 3. And because we're asked to find it in the exact value, we don't want to convert this into a decimal because it would be a recurring decimal. We actually want to leave it like that as a fraction. So these are our two values. This was the area under the trapezium, and this was the area under the curve. So now we're going to look at part D, and part D is finding to one decimal place the area of the shaded region on the graph. So that's the area between the line AB and also between the curve. So part D. And so really all that is, it's using compound areas. So we've got the area under the trapezium, and then we're just going to subtract from it the area under the curve. So this is just 52.5 that we had before, minus the 95 over 3. So if I put that into my calculator like that, that will give me 125 over 6. And if I use the SD button on the calculator and round it up to one decimal place, I get 20.8. And that's it.